So welcome to Azure Conf. My name's Chris Auld. I'm from sunny New Zealand down in the South Pacific, although it's kind of winter there at the moment, so it's a little chilly. This session's about the new Windows Azure document database that's in public preview. We're going to try and do a bit of a deep dive on that, so cover some topics that you might not have seen already. It does mean I assume a bit of sort of prior knowledge in that, so we're not going to go into sort of the basics in a great level of detail, but we'll do a bit of a refresher. So we'll go quickly around, what Azure Document DB is, its capabilities, its characteristics, and so forth. And then we'll have a look at how it's paid for, and in particular how it's metered and billed, so that you can understand, what you need to think about when it comes to provisioning capacity, using that capacity, and also tuning your database to be able to make the best use of your resources. We'll talk a bit about polyglot persistence. Now, I expect that many of you have heard of that already. It's all about how do we use multiple databases to back end our application so that we can basically take advantage of the best capabilities of the whole stack. And we'll also talk a bit about data modeling. So how do we model our data in this document database world? And I think it's really important that you go away understanding that it's not about just bringing your relational database model and slapping it into a document database. We'll talk about a wonderfully polarizing topic called data tier programmability. This is all about having the power of things like stored procedures, triggers, and user-defined functions inside your NoSQL database. And then we'll finish off talking a bit about consistency. So when we work with NoSQL databases, we're usually dealing with something that's running as a replicated database with copies of our database on multiple servers. And consistency trading is all about thinking to what extent are we prepared to trade off absolute consistency across those replicas for maybe some improvements in overall performance, latency, or scale. So let's get into it. So if you missed the memo, we're going to have a quick run around DocDB. Great thing about Azure, and in fact many of these cloud platforms, is they just ship stuff so fast that actually they don't usually have the whole hoopla of big PR type launches. This stuff just sort of ships and usually gets announced on maybe Scott's blog or something like that. So maybe you haven't heard about Document DB yet. So we'll do a quick lap for you. So Document DB is a fully managed, highly scalable NoSQL document database service. What does that actually mean? So it allows us to store JSON documents inside a store and have those indexed for us and be able to query them back out. But the really neat thing is that it's completely schema free. So we can stick any document we want in there and it will be indexed such that it can be efficiently retrieved. It's transaction aware and it has server-side programmability. So we can actually run JavaScript in the data tier. Right? We can execute that JavaScript, we can perform operations against multiple documents, and those will be done inside the context of a transaction. Right? So we can make multiple changes across multiple documents and then succeed or fail that whole transaction. Pretty neat, pretty unique across the market. It runs as a service in Windows Azure, but it's running on specific right optimized hardware SKUs. It uses SSD for its storage. And we can tune the indexing and the overall database consistency to meet our application requirements, as well as our desire for say cost savings and so forth. It's been built from the ground up to be delivered as a service, and I think that's really important to reinforce. Right? So this thing has actually been designed to be delivered as a service and to scale in nice, small, incremental chunks from the outset. It's not just picking up an existing piece of software and chucking it in the cloud. So you pay for it as you go, and it really does let you achieve a much faster time to value. Right? And that's actually becoming really important as we build applications. How quickly can we achieve value? How quickly can we get our application to market? So DocDB in one slide. Surprise, surprise, it is a RESTful service, right? So it's a RESTful model and you access everything over HTTP. using HTTP verbs against URI endpoints. That means that access can be from any client that supports HTTP, which is pretty well everything. Right? And you can either write those RESTful calls yourself, or you can use some libraries that have been provided by Microsoft, and they include support for things like Node, for .NET, for Python, and for JavaScript. As I said before, it's all based around URIs. So every resource inside Azure Document DB is addressable by a URI. It's partitioned for scale out and replicated for high availability, right? And we can tune the consistency model to trade off performance and latency against consistency. It has a granular access control mechanism that allows us to apply item level permissions to the various resources that we have inside our database accounts. And it has a mechanism to support attachments, and those attachments are automatically managed for you into Azure Blob Storage. And we'll have a look at that in some detail later. As I said before, it has T-SQL-like programmability. So that means we have things like stored procedures, triggers, user-defined functions, stuff that should be very familiar to people who are coming from a relational background. And then you basically buy storage and throughput on a capacity basis for your account, and you can consume it in reasonably small chunks as you scale your application. So let's start by talking a bit about how we go and buy Windows Azure Document Database. There's so many services in Azure, I keep on getting them mixed up. So, you purchase things called capacity units, and you purchase a capacity unit as part of your database account. At preview, we can purchase up to 5 capacity units, and it's about $22.50 with that 50% discount per capacity unit. If you really need more, I'm at CAULD on Twitter. Just hit me up and I'll put you in touch with the people who'd be more than happy, I'm sure, to sell you more capacity units. So a CU is a reserved unit of storage, so you get a certain amount of storage in gigabytes, and a reserved level of throughput capacity that's described in a thing called request units, and we'll have a look at request units shortly. It's important to know exactly how capacity units get spread out across your database and across the collections that sit within your account, because that's really the important thing that we're dealing with inside our account, is this idea of collections. And the collection is basically our unit of scale. So the reserved storage gets allocated automatically across those collections, but it's subject to effectively a minimum amount of 1/3 of the capacity unit per collection and a maximum amount of 10 gigabytes, the whole capacity unit per collection. Similarly, our throughput, so our reserved throughput request units, also get automatically applied across our collections, although in this case they actually get split equally across however many collections we have running within our database account. Again, we're subject to a minimum level of 1/3 of a capacity unit, 667 RUs, being applied through to a whole capacity unit. If we end up going at our database with a throughput level that is greater than our provision level, we are going to get throttled. So let's talk a bit about those request units. So when we purchase a capacity unit, that comes with a provision of being able to execute 2,000 request units per second against our document database. That effectively means that if we've got a single capacity unit applied, we need to keep our throughput below that 2,000 request units per second. Otherwise, we're going to get throttled. When we get throttled, we get sent back an HTTP 429. The client libraries that are provided, they catch that, right? So they'll catch that. They'll look at a thing called the retry after header, and that basically specifies a number of milliseconds that you need to wait before you go hitting the server again. and the .NET Client SDK catches all of these for you, and it will do these automated back off and retries. You probably also want to make sure you set up some alerts in the Azure portal so that you're notified if you do get throttled. So request units are a pretty important concept, and they are an abstract concept, right? So we can't say a request unit is a certain amount of CPU or a certain amount of RAM or anything like that. They are an abstract concept, but the important thing to realise is that given the same database, right, so with the same data in it, with the same indexing set up and so forth, you should get a consistent level of request units consumed for a given operation. So that allows us to do our planning. To give you a rough idea of sort of request unit consumption, based on a database containing documents of roughly a kilobyte with 10 unique properties, with the database consistency level set to session, and all the databases automatically indexed, these are the rough numbers of request units you can expect to burn through for typical operations. So pulling a single document by itself link, it's going to rip through one request unit, right? So that's effectively your smallest, sort of most atomic operation you can perform. That is the simplest operation that you'll be performing against the database. Going up from there, if we think about things like inserting, replacing, deleting a document, they're going to rip through 4 request units. So, whereas we could do 2,000 self-link reads, we can only do 500 insert, replace, deletes for the same amount of capacity. Querying a document, so querying a document out of a collection using a simple predicate query, it's going to consume 2 RUs. So again, half the throughput that we'd get if we were just using that self-link. And then, something a bit more complex, say we used a stored procedure, and within that stored procedure, right, so single call to the server, the stored procedure then does 50 document inserts. So again, we end up with 100 RUs. So, again, we see our level of achievable throughput changing. So let's have a look at actually how you understand these RUs and how you can pull RU information back as you're working with your database. So the request units come back from all of your queries as headers, right? And we can actually have a look at those headers. You can either pull them off the requests inside code, or what I'm using here is a tool called Azure Document DB Studio, and I'll give you the link for that shortly. But it's a really useful little tool that you can use to connect up to your document database and have a look around. So I've got some collections here, and we're just going to have a look at this first collection called Sessions and run some queries against that. So let's jump in here, and I've got some queries I prepared earlier. So this has just got some documents in it that describe conference sessions. So let me run this one, and this is that simple predicate query. And so you're saying, I reckon I got a pretty good idea of what that's going to cost in terms of request units, because it's probably going to cost 2 request units, right, as we saw before. As we get a bit more complex, you're going to start to see those numbers change, right? So let's do another query that again is querying that same collection on that same property, but in this case I am using some ORs. So I'm actually going to be querying for multiple values of that property. And you'll see the data's coming back here, and I can browse that as hierarchical JSON. But the thing we're looking at the moment is these request and response headers. So you'll see here's that x-ms-request-charge, say that quickly 5 times, header, and that comes back from every request, and that gives you the number of request units that you burnt through. Now you've got to be a little sophisticated in terms of how you work this out, right? Because if you remember, request units that are applied from your capacity unit come at effectively 2,000 per second per capacity unit. So if you've got queries that are running for quite a long time, you'll need to think about, the request units that I burn through, how do I amortize those out across the length of time that the query took to run. So this one was 6.1, and then let's finish with a query that's running 2 separate predicate comparisons. And you'll see, that's slightly quicker. So that should give you some idea of the, how quickly we burn through these resource units. And we'll have a look at some more of those when we talk a bit about indexing. So that tool I was using was called DocumentDB Studio. It's up on GitHub. You can grab the source code. If you've got your smartphone, snap your screen or punch that tiny URL into Internet Explorer and go pull it down. Source code's there, and it's a super useful tool for just faffing around with your database. So we have this true schema-free database. I think it's really important to re-emphasize this is a true schema-free database. And what do I mean by that? At the end of the day, these things run at scale. And if the only way to get your database to run properly at scale is to apply indexes to it, and the only way to have that indexing is to manually define those indexes, then the mere definition of those indexes actually implies a schema. And that's a real problem, right? Because it means that you're no longer able to take advantage of that very flexible data model, which is what you really want in a document database. And we'll see a great example of that later on. And so I think it's super important to reinforce that with Azure Document Database, you get fully flexible schema-free indexing as well as schema-free data storage. So by default, everything is indexed. Those indexes are schema-free, so they do not mind what you put into your collection. There's a whole bunch of interesting magic that's come out of Microsoft research that's actually driving this indexing mechanism. It's not B-trees, and it focuses on working really well under strong write pressure and at scale. And I know that the team would not let me tell you more for Azure Conf, because they're working on some information to share exactly how it works a bit more broadly. So, out of the box, it just works. But it can't read your mind all of the time, right? So everything is indexed, but everything is, is at the moment hash indexed, right? Because we don't know if you want to treat a certain property as a range or a hash. So there are still benefits in defining some indexing optimizations in some situations. But again, I reinforce, by default, everything's indexed, and for the most part, it just works. So we can tweak, change, modify the way that DocumentDB applies its indexes. And if you've got any sort of background in databases, it's the same sort of trade-offs we've been making for a long time. So what are we trading off? We're trading off things like write performance. How long does it take to write? Right? The more indexes we have, the more properties we're indexing. For the most part, the longer and more RUs it uses to write. How long does it take to read? Again, as a rule, the more properties that are indexed, the more flexible our queries can be and still run at high performance, the lower the number of resource units required. We obviously want to avoid queries that are going to force a scan. And in fact, Azure Document Database makes you opt in to performing a scan. If you run a query and it thinks it's going to have to do an index scan, a collection scan, it will warn you, it will raise an error, and you actually have to specifically opt in to having the database engine perform that scan, because it's a very, very expensive operation. What else are we trading off? We're trading off storage. So how much space does the document and the index require when we store it? The more we index, the more space we're going to end up using to support that index. And complexity and flexibility, right? As we end up customizing, modifying, and tuning those indexes, we move away from that pure schema-free model. So we are making trade-offs. How do we configure the indexes? So we do that by setting a thing called an index policy. And the index policy allows us to define a set of rules for indexing on that collection. I think it's really important to reinforce this is defined on a collection, and at the moment it is immutable. So when you create your collection, you define the policy and you can't change that policy later. So it's a bit of a gotcha, so you just need to make sure you're aware of that. That policy then defines an index mode. That mode can be consistent or lazy. Consistent means that as we write the data into the collection, the index is written at the same time and those are kept consistent. So if we go and make a query, goes and hits the index, it follows the consistency level of our database. Lazy is as lazy sounds. Am I allowed to make jokes about Australians here? No, okay, I won't make jokes about Australians here. So lazy is, sorry, I'm from New Zealand, as lazy sounds. It means that as we write data into the data store, that's not going to be added into the index immediately. It's all going to happen in the background. So that's index mode, which is effectively index consistency. We then have this property called automatic. So automatic is defining exactly how Azure Document Database writes data into the index. So we can set automatic to true, and that means every time we write a document, it's automatically going to be added into the index. Or we can set it to false, right? And that means that every time we write a document, we have to specifically opt in to that document being added to the index. And you think, why would I want to do that? Well, a really good scenario is to remember that collections inside a document database are not like tables. They're going to contain all sorts of different documents, and you may well want some of the documents that you put in there to be indexed and some of the documents that you put in there to never be indexed. Right? So by setting automatic off and then using an indexing directive when you put documents, you can opt just a subset of your documents into being indexed, and everything else you can retrieve via the self link. Remember, that's that really fast get operation, right? And that way you can push documents in to be indexed and then maybe have some other documents that you're referencing only ever by the self link. So we've got our mode specified, so that's going to specify that we are going to do consistent indexing. We're going to do automatic indexing. What we get to specify now is paths. So effectively, we specify paths, and they get mapped down to documents as we insert documents into the collection. And that allows us to include and exclude portions of documents from the index. So we can include a specific path, we can actually then exclude sub-path portions of that included path, or we can exclude specific paths. When we include paths, we can choose whether we want to use a hash index, which is the default, or we can choose to use a range index. And they are as they sound. A hash index is ideal for single key lookups. A range index is ideal for pulling a range of values. So you'd use that on things like, dates and so forth. Important to note that at preview, there's no support for range indexes on strings. So if you are going to do dates, you really want to turn those dates into a numeric value and then put a range on them if you need to be able to pull those in a range type fashion. The last thing we specify is we specify precision. And this is basically telling Document Database how much of our property value do we want it to pull into the index. That obviously affects storage overhead, right? But we need to have a sufficient amount of data to make the indexing sensible. If you've got values that are basically, almost entirely the same, right? Particularly in that first portion of the values the same, then you need to make sure that you have a larger precision value so that you capture sufficient entropy to make the index work sensibly. And it's, again, a bit of an art to get that right. So the more data you've got in your database and the lower the entropy of your values, the larger the precision level is going to be. As we increase the precision level, we're obviously trading off storage, and we're trading off the number of request units we have to use to actually write that data in. So let's have a look at indexing. So I've got 3 collections defined here in my database. the one that we're having a look at just before, called sessions. And then I've got two others with slightly different indexing policies. So the sessions index policy precision, right, is using automatic indexing, consistent indexing mode, but I've changed the string precision from the default value of 3 down to a value of 1. The index policy lazy, I've changed to just be lazy. So it uses the default paths and the default precision values, but it's going to use lazy indexing instead of consistent indexing. So what we'll do now is actually have a look at what does that do in terms of impacting our usage of request units as we apply queries to create documents inside those collections. So if we start with the sessions collection, and I'll just grab a document from over here. So you'll see that consumed 24.5 RUs to write that document into the session collection, which is using the default index configuration. What if we now go and write that into the one where we've lowered the string index precision across the entire path range? Okay, so the last one was 24.5, this one we're consuming 23.5, right? So you'll see that by lowering that precision, right, we've maybe taken, you know, maybe a 2 or 3% off our consumption of RUs. So not a huge amount, but again, you know, this is all about probably experimenting and working out what your trade-offs are in your particular application circumstances. What about if we actually go and effectively turn real-time indexing off, so move to using lazy indexing? So you'll see now we've got a significant drop in our use of RUs, right? And that's because it's not having to go and update the index. And what this tells you is, you know, actually there's a significant amount of work in doing that, you know, that index update. So, you know, there may be scenarios where you say, actually, I do need to be quite aggressive in terms of how I change and configure my indexing for that particular collection. It also means you probably want to be smart about using multiple collections within your database to be able to specify different indexing policies for different sort of types of documents. Now let's talk about this thing called polyglot persistence. When we think about the types of applications we build now in sort of this era of modern cloud applications, in many cases it's actually about bolting together a whole lot of different services rather than maybe building stuff from the ground up. And so most, in fact, I would probably hazard to say all modern cloud applications are going to use a number of different data stores to store their data. At least two, probably several. One of the key guys behind this idea is a guy called Martin Fowler. I suspect that many of you have heard of him from his book Design Patterns, and he's got this book called NoSQL Distilled that I commend to you as a good read. QR code there to go grab it. But it provides some really good background on the characteristics of different types of NoSQL data stores, as well as strategies for combining those together. If we think about Windows Azure, we've got a number of different data stores available to us. We've got the classic SQL Server relational database, available in a couple of different variants. One is running at ourselves inside a VM. The other is running it in the context of Windows Azure SQL Database. But that's going to give us, you know, fully featured relational database characteristics, you know, full transactional processing, rich queries, really extensive tooling support, and so forth. If we think about the other end of the spectrum, we've got things like blob storage, right? Blob storage, super simple, binary object storage, able to scale to massive scale, inexpensive, easy to access, schema-free. So that's going to be really useful for stuff as well. Similar to that, we've got table storage, so a slightly richer type of storage abstraction built on top of the same underlying storage technology as blob storage. And then document DB sort of sits somewhere in the middle. So we've got some of those characteristics we've come to expect for relational databases, like transactional processing, like rich querying, but it also gets some of those characteristics of the pure cloud play services, right? So it's run for us and managed as a service. We're able to scale it elastically. It's got a schema-free data model and so forth. And so, with any modern cloud application, you're likely to pick a number of these different data stores to build out your application. And DocumentDB gets this, all right? They've built in capabilities to support this type of polyglot persistence. And one of those is this thing called attachments. So if we think about document database, $22.50 gets us 10 gigabytes of storage. That's quite a lot more expensive than, say, blob storage on a per gigabyte basis. So you want to be sensible about how you use that, right? You're not going to stick 3, 4, 5 megabyte images into your document database. Why? Well, because you're not going to be able to index them for a start. If you're not indexing them, they probably don't belong there. Instead, you'd probably store those into blob storage. Now, you could do that yourself and manually manage URLs and so forth. But DocumentDB actually provides a managed attachment mechanism that allows us to submit those image files through the DocumentDB service and have the DocumentDB service manage those for us inside Windows Azure Blob Storage. At preview, you get a couple of gigs of storage provided as for each of your DocumentDB accounts. And when you store through that mechanism, DocumentDB manages the life cycle. So if you have attachments on a given document and you delete that document, Azure Document Database will go and delete those attachments out of blob storage. So it manages the life cycle for you while allowing you to take advantage of the lower cost storage in Azure Blob Storage for stuff that doesn't necessarily need to be indexed. Attachments also provide a self-managed mechanism where if you do want to store the content in some other type of service, you can still use attachments, create the attachment, use all of the metadata storage, but you'll need to provide the URL of your content. You'll also need to manage that life cycle in terms of deleting the attachment on document delete as well. So let's have a quick look at that. We'll crack open Visual Studio. And I've got a little console app here, and we'll chuck this up on the Azure Conf site for you to pull down and have a play with later. But I've got some code here that's going to run through and create an attachment for us. And I've got some breakpoints in there so that we can step through it. So what I'm doing here is I'm now going to create some documents for speakers. So at the moment I've got sessions, I've got tracks in my data store. In this case, I'm going to create a new document for a speaker. It's a pretty simple document, it has a single property called speaker name. And what I'm then going to do is I'm going to go and attach a file as an attachment to that document. So I just go and pull that out using a file stream. I can then create that attachment up in Document Database. And then I'll go and query that back out just to show you that there's no smoke and mirrors here. So if I go and pull that back out, so I'm basically pulling now each attachment for my document. So each attachment for my speaker name Crystal document. Reading that attachment back out, so reading the binary data back out. And then writing out the attachment name and the length of the binary data that I got back. And then the last thing I'll do is if I go and delete that document, right, that's actually now gone and deleted both the document and the associated attachments out of DocumentDB and out of blob storage. This is actually providing a built-in mechanism to support polyglot persistence patterns within Azure Document Database. So when we think about using a multitude of data stores, we need to come up with some strategies and decide exactly which stores we're going to use when and where. So there are a few things to think about. How much storage are you going to use? Where is that storage going to live? And what does that storage cost to use? There's a really big difference in terms of the per gigabyte cost for these different types of storage. So you want to be making sure that you're being sensible about which storage you use for which types of data. How is your data being indexed? Is it going to be indexed at all? We're probably not indexing JPEG files. So therefore we probably don't want to put them into expensive indexed storage running on SSD drives. How much entropy and precision do I have in my data? Will it ever be queried? Should I exclude it altogether? When I need to go and retrieve that data, how many network calls do I need to go and make to retrieve it? If I've got this polyglot persistence pattern running and I've got the data for my e-commerce product spread across 4 different data stores, then potentially I have to go and make 4 calls across the network to go and get that single view of a product that in the past I might have pulled from a single or maybe a couple of locations. So I'm trading off some savings probably at operations time in terms of using cheaper data storage with some additional complexity in how I implement the solution, but also in terms of how I manage it. Right? Again, if I've got my data spread across multiple data stores, I have to back up all of those data stores. I also run into the challenge of consistency. If my data is spread across multiple data stores, it's probably never going to be completely consistent. All right? What I mean by that is if I'm going to go and write out to all those 4 data stores, there will be points in time where I've only written to say 2 of the 4. So these are things that you're going to run into. They're going to present challenges, but I think you'll find that particularly as you move into really large scale applications, there are huge benefits in taking full advantage of highly optimized data stores for different parts of your application. How do we model data for the document database? It's really important to understand that you don't want to treat a document database like a relational database. And it's pretty easy to do that, right? You say, okay, I'm going to have a products collection and a manufacturer's collection and an orders collection, and you basically build a relational database. There's a whole lot of problems you'll face there in terms of a collection. A transaction can't span multiple collections. It's the wrong way to model. What you should instead be thinking about is how can I place related but different documents within a single collection? Or indeed, how can I turn my data into a single document and store the whole lot together? And so that really brings us to talking about embedding versus referencing in terms of our data structures. And some people call it sort of denormalization and normalization. I'm kind of reluctant to call it that because normalization has quite specific characteristics in relational land. But embedding is basically treating our document as a hierarchical data structure. And obviously we can do that, and it's a sort of a unique characteristic of this type of data store. Alternatively, we can split our manufacturers out here, and instead of embedding our manufacturers inside the product, we actually run a separate set of manufacturers and provide a link between the two. And there's no right or wrong answer here. They're well suited to different things. So embedding is well suited to containment scenarios, right? Typically where we are dealing with, 1 to a few pieces of associated information. Typically we were dealing with slowly changing data. So stuff that we're not updating all the time, and certainly stuff that we're not adding lots and lots of new entries to in a potentially unbounded fashion. If we do many-to-many here, it does mean that we're going to need to manage duplicates, right? And for most people coming from a relational background, duplicates is kind of a no-go area. But actually duplication is really useful in terms of getting the best out of what we build. With embedding, we need to make one call to read all the data. All right? So it means that we're probably going to be quicker at read time. But if we need to write any one piece of that data, so if we need to make a change to the manufacturer, we're going to have to go and write the whole product document with the manufacturer embedded, right? And if that manufacturer is actually included in multiple documents, we're going to have to go and write the whole of multiple product documents in order to update that, right? So again, we're making these trade-offs. If we think about reference type modeling, that is probably closest to your idea of the database third normal form. It provides a many-to-many mechanism without duplicates. It allows us to have that unbounded idea of one-to-many, where the many is unbounded. But what are the trade-offs we make? Well, it means that we have to make multiple calls to read all that data. Although hold that thought, because we'll have a look at programmability shortly. But it does mean that we can make a single write call to update any of those referenced documents. So when we're doing these relationships, how do we do those? Firstly, how do we actually make that relationship? How do we make the link? In document database, we have a couple of fields that are pretty good candidates for this. The first is a field called ID, and this is the unique but user-generated identifying field that's able to be placed on every document. So we enforce uniqueness. But it is just a standard property. The other is to use the self-link. To a degree, it's a matter of taste, but the important thing to remember with the self-link is that it is the most efficient operation that we're going to be able to perform against our database. Right? It uses a low level of request units, and therefore, if we can get away with using it, right, i.e. if we're happy to have the self-link rather than sort of the human-readable identifier, it's going to be more efficient in the long run. So the next thing we need to talk about is the direction of that relationship, where we put the relationship identifiers. If we put them in manufacturer, we're going to need to go and update manufacturer every time we add a new product. And product is basically unbounded, right? So it means that our manufacturer document risks getting very large, and given we have to rev the whole document every time we add a new product, it's probably going to cause problems. On the other hand, if we put the link into product, so product refers to manufacturer, it probably works pretty well, right? The only time that we've got to update the manufacturer link is if the product changes its manufacturer, and so that works out pretty well. Manufacturers for products are typically bounded, and in most cases bounded to 1. Right? So I think that approach probably makes good sense in this scenario. There are actually going to be times when we'll want to go in both directions. Right? We'll want to have links from both, say, manufacturer to product and from product to manufacturer. And we'll actually talk about one of those shortly. So that brings us to talking about the canonical polyglot persistence scenario, right? Which is the online store. Anybody who's ever talked about polyglot persistence will have talked about an online store. There's a great example from the Patterns and Practices team. It's referenced extensively in Martin Fowler's book. Let's go through and actually think about some of the data modeling challenges you might see when you think about a product catalog. So here's a high level sort of set of data characteristics that you might need to represent in a product catalog. So we've got our name, right? We probably almost certainly want to search our name. Hash index is probably fine. We're probably not searching on a range of names. But we probably also want to duplicate that into maybe something like Azure Search, right? Because document database doesn't provide full text search. It provides hash indexes for exact matching and range indexes. What about the SKU? So for most product management systems, the SKU is a really important lookup field, right? You need rapid lookup by product SKU. If we look at our SKU here, it's in the format of year, so probably the year the product was added to the catalog, some sort of category identifier, and then some sort of unique identifier about the product. The challenge we've got here when we think about how a document database manages its indexes is that we don't have a lot of entropy in the front end of that property value. So what could our options be there? We could increase the precision, or we could also do some other things. We could actually reverse that whole skew value. So we could reverse the skew and insert the skew reversed, which would push the 53431 portion of that skew value into the front of our string and make that the portion that's actually been indexed. It would give us better entropy in our index and improve the index performance. That obviously means we then need to remember all through our application that we've got a reversed skew. The other option is we could actually duplicate a reversed value. We could include the reversed value in our index and exclude the non-reversed value from the index. Another thing we might like to do is we might like to actually pull that year out, because we may well want to be able to do range-based searches on the year. All right, so we might pull the range out to another field and add a range-based index on that. What about the description, right? So a big 8K chunk of HTML. You probably would want to index this in something like Azure Search for full text indexing. You probably don't want to index this inside Azure Document Database. We could be really aggressive in terms of saving space and actually push that description out into an attachment, right? But that would mean we're then making multiple calls up to the server to pull the whole product out, right? We need to go and pull the standard product metadata and go and pull the attachment separately. So, you know, probably a line call as to whether we'd do that. Really comes down to how often do we retrieve the product information without the description. But yeah, we almost certainly would want to exclude that from document DB indexing. What about currency, right? So if we need to store an amount and a currency, that allows us to have multiple base currencies inside our product database. We probably want to embed both of those inside as a sub-portion inside our document, right? That means we're going to be duplicating those currency identifiers. That's probably okay. Why? Well, it's a slowly changing value, right? Currencies don't change that often. I think the Scottish just about changed their currency, but they decided better of it. You know, but again, it's a slowly changing value, and there are big benefits in being able to go and pull all of that information out of the database in a single call. We probably also want to push some of this data across to search, but on the basis that we're working with currencies, we probably want to have localized data into search. That in turn brings a whole lot of consistency challenges, right? If we're storing currency information inside our document database and we are determining product prices dynamically on the fly using currency exchange rates, we're going to have consistency challenges with the data that we need to push over into Azure Search. Images, hopefully it's pretty obvious now, they're going to go into attachments, right? And the nice thing is that Document DB is going to manage the life cycle for us in terms of when we delete a product, it deletes that product image. What about reviews, right? So we've got a whole range of options with reviews. We could embed the reviews. That's probably not a bad idea. Reviews aren't usually too long, although if you read some of the reviews on some of the e-commerce sites, they tend to be a bit of a treatise, the odd humorous one. So we could embed them. But then where would we embed them? Or where would we reference them? Do we reference and embed them on the product? Do we reference and embed them on the reviewer record? Do we reference and embed them on both? Or could we come up with some hybrid approach? So an interesting approach might be to embed them into the product, but only embed the most recent 10, and then reference the remainder, right? So that way we could pull the whole product record out, including the most recent 10 reviews, and when you hit the More link, we actually go back and we pull the data out of the database once again. And again, we'd almost certainly push some of these across to search. And then product attributes, and this is really where we see the full power of that schemaless database. It's really where we get to see exactly how deep the rabbit hole can go. So let's have a look at some sample JSON. So here's some example product JSON from a company called AdventureWorks, and you may know AdventureWorks because they've been around for a wee while. So this is representing a mountain bike. Right? So you'll see we have the pretty sort of common stuff through here. You'll see there's that price example, right? So we've got the price amount, and then we've got that sort of complex type representing the currency embedded inside the document. Right? You'll see we've got something similar when we discount. Colors, sizes, again, you may think, do I do those as references? Do I do those as embedding? And then we come down to product attributes. And I'm a bit of a mountain bike geek, so this probably shows a little bit of my geekery. But this really allows us to see the full power of that schema-free database, and that these are strongly typed product attributes. And this is a really hard problem to solve when we think about a relational database, in that we have to build extremely complex normalized models in order to be able to represent these while still allowing us to index fields appropriately based on their type. Because you'll see here that we've got a number of attributes that are just string values, but we've got an attribute down here for the weight of the mountain bike that's actually a numeric value. Right? So we might want to be able to say, find me all mountain bikes that weigh less than 3.5 kilos. If we want that to work efficiently, we need to be indexing that value. Fortunately, with Document Database, we have that schema-free data storage and also that schema-free indexing. So it means that we can actually go and get really, really complex. So here we're representing the drivetrain of the mountain bike, that's its gears and so forth, right, with an even more complex embedded set of data, right? So we're actually representing the drivetrain as an array of more complex objects, which can in turn also contain an array of complex objects, all of which can have their own strongly typed values, all of which will be indexed. So literally this would allow us to build a rich search engine where we could say, find me mountain bikes with alloy cranksets that have chain rings with more than 42 teeth, right? And actually be able to express that and have that executed at the data tier level and retrieved efficiently because we're indexing the whole data set. And so that's really the power of being schema-free, right? It allows us to fully index those complex type structures. And it means that we can then define our schema independent of the data store itself. And we can then use that schema that we've decided to use to model our data. We can use that to drive things like dynamically building filter forms, dynamically building editing forms, to create templates to take the JSON that comes out of our data store and render it into HTML. And a couple of really cool examples where I think this is the sort of, there's huge potential here around things like material safety data sheets. So here's a material safety data sheet. And you'll see it as a document, right? But it's a document that contains a whole lot of stuff that is quite structured and typed data, right? Now at the moment, if you just have this as a PDF document, it's impossible to actually query it in that rich, you can't query against the rich data. And a way back a long time ago, I actually built an interesting system that that goes part of the way there for some of this stuff. And it's actually based around XML, and it gets shredded into a relational database, unfortunately. But this toxin site has really, really complex data structures. And the power of document databases will allow us to represent those complex data structures and still index them as strongly typed data, right? So it means that we would then be able to look for things oh man, where is it? This is a big data set, right? So these are really important values, right, that talk to the toxicity of acetaminophen, paracetamol. Being able to represent those as strongly typed data inside our database and be able to search on them as strongly typed values is hugely interesting when we think about the sorts of very complex data sets that we need to deal with when dealing with things like chemical substances and other materials. So it's not just about building online stores. Okay, I thought we'd leave this topic towards the end because it can be a bit of a sore point. Data tier programmability. If you've spent some miles in a relational database, you've probably done some data tier programmability. If you've spent any time in the development community in the last 10 years, you've probably also run into the odd person who seems to think that data tier programmability is not a particularly desirable thing. I beg to differ. So document database provides programmability inside the data tier. This is going to be really familiar to those of us who come from a relational background. It allows us to run JavaScript code within the context and on the servers of document database. We can run stored procedures, we can run user-defined functions, we can run triggers. That code runs within the context of an ACID transaction. Right. Now these are not multi-statement transactions. Every time we make a call to Azure Document Database, that call is wrapped inside a transaction. If within that call we throw a JavaScript exception, that whole transaction is rolled back. Our code runs within a sandbox, right? So we have a few limitations. There are no imports. We can't make any network calls, can't use the eval statement, and we will be resource governed and time bound. But it does give us a very, very powerful model. So let's have a look at some of those running. So again, back over here in my quick demo application for you, and we will give you this code. I've got some user-defined functions, some triggers, and some attachments. So let's start with the user-defined function. So what that's going to do is actually go and pull information about the sessions in my conference session catalog and actually have a look at the time the session's on and return a value indicating whether or not I've already missed that session. And so you'll see that we've missed pretty much all of the sessions except DB319, which is the one that I'm currently presenting to you now. In terms of how that works, so here is the JavaScript for our trigger, right? Sorry, JavaScript for our user-defined function. So we define the function have I missed it, takes the date. We then need to do a little bit of date jiggery pokery because again, without includes, it's harder for us to pull in some nice JavaScript date manipulation libraries. But that then allows us to basically augment our data using that user-defined function from within any query. And so if we have a look at that UDF actually being used within a query, so here you'll see me creating that user-defined function inside my collection. And then here you see me writing a SQL-like query against document database calling my am I too late function, passing in that session start date. So again, should be super familiar to anybody who's worked with relational databases previously. Okay, let's run that up again. and let's have a look at triggers. So what we're doing with the trigger is we are using it to set a last updated value on our record, right? And again, there's all sorts of uses for triggers. You might use them to write some journaling entries, to have some background processes running. There are some important things to understand with triggers inside DocumentDB. Our trigger's pretty simple, right? We're able to get a context object and a request object that lets us on this pre-trigger access properties of the data that we're trying to change. So in this case, we're going to grab the document that we're endeavouring to save from the request body, and then we're going to set the last updated value on it based on the current time, and then update the body that's actually saved. Right? So, it's pretty simple to actually write one of these triggers. The key difference that is sort of probably starkest in terms of how triggers work in a relational database and how triggers work in document database is that we need to opt in to the trigger being executed when we call up to DocumentDB. Right? So when we make the request to create our new document, we're actually including in the request options that we want to run this pre-trigger. Now the reason that you'd want to do that really comes down to this idea of collections, right? So a collection is going to contain all sorts of different documents. So you probably don't want to force the fact that a trigger runs every time you touch something in a collection. Right? Instead, you probably want to be able to opt in and only have that trigger run when you perform certain operations, when you typically update certain types of documents into your collection. And then let's finish up by looking at a stored procedure. So the stored procedure we're doing here is actually helping us to solve that multiple calls to the database challenge, right? And that is that where we've got reference data, we need to go and make a call to pull, say, the session, and then we need to make a call to go and pull the track, right? So here you'll see we've pulled the session, here we've pulled the track, and we've done that with a single call to the service. So what we've done is we've basically gone and pulled two documents and combined them together. All right, and so here you'll see what we're doing is we're pulling the session, then we're pulling the track, and then we're basically writing out an alternative response, right? Rewriting our own document structure to be returned back to the client. And again, what this is allowing us to do is to reduce the number of round trips that we have to make to the server. And so that's a really important thing to realize with programmability in the data tier with document database. Again, gets a hard time, right? Stored procedures, triggers, get a hard time. What are we actually using this for? So we're using this for things like reducing network calls, right? Because a really expensive thing for us to do is to go and pay that multi-millisecond hop across the network, right? So if we've got data structures that use reference documents rather than embedded components, we really want to minimize the number of calls we make across the network by potentially using a stored procedure, a little bit like a parameterized view, and returning all of that data in a single call. We use programmability to run multi-document transactions. So if we want to have something all succeed or all fail on an atomic basis, then we can use a stored procedure to do that. Pass the whole lot up into the stored procedure and have the stored procedure shredded out into multiple documents and so forth. Again, the context of our transaction is a single collection, all right? Don't treat a collection as a table, right? A collection is going to have all sorts of different types of documents in it. transforming and joining, right? So that's what we saw the stored procedure used for in this example, right? We saw it pulling data from the tracks document, we saw it pulling data from the session document, combining that together, and returning that back down as a transformed document to the client. And then, triggers really useful for driving lazy processes, and lazy processes are pretty important in this polyglot persistence model, right? So if you think about the idea of we update a product, and then we need to go and update, say, search or some other type of data store, we may want to run that as a lazy process where we actually write out some data to a journaling table and then have a background process that watches that journaling table, picks it up and brings our data in the overall system back to consistency. So that brings us to talking about consistency. I'm not going to go into a whole lot of detail today on replicated data consistency. I think a really good paper to read is this one by Doug Terry from MS Research called Replicated Data Consistency Explained Through Baseball. Now, being from New Zealand, I'm more of a cricket player, and I will admit that the Australians are quite good at cricket. I thought I'd better give them one back from the joke earlier on. But that document's well worth a read, and there's a QR link for you to go and grab it there. Tuning consistency is all about deciding on the extent to which we're prepared to deal with inconsistent data across the multiple replicas of our data that the system runs in order to maintain availability and throughput performance. And Windows Azure Document Database allows us to specify that our account run at a default consistency level, and we can choose one of any 4 of these consistency levels. So if we start with strong consistency is basically guaranteed consistency. That means that any time we write to Azure Document Database, it is going to write to a quorum of replicas. All right, so say we've got 3 replicas, with strong consistency we're going to write to at least 2. Right? And then we're going to read from as many replicas as we need until we get a quorum of answers back that are the same. So we've written to 2, now we go and read, and as soon as we get 2 values back that are the same, we know we've got the strongly consistent piece of data and we can return back to the client. So it's called quorum writes and quorum reads. So then we have bounded staleness, and bounded staleness basically lets us say that we're prepared to have data that is a certain amount of time or a certain number of operations out of date. Session consistency is the default for Azure Document Database. And session consistency is basically read your own writes, right? It keeps us from having a situation where we end up with phantom reads. So what session consistency does is it uses asynchronous replication for writes, but it uses session-bound consistency for reads. That means if we write a piece of data and we go and read that data within the same session, we are going to get a strongly consistent database. However, to someone who's outside of our session, they're potentially going to get a weak consistency type of database. And that works pretty well. If you think about, common scenarios, that's going to work quite well. If I'm writing the data, I expect to get the same value back. However, if I'm just reading any old piece of data, I probably wouldn't notice the change, right, if I got some inconsistent data back between 2 calls. And then we have pure eventual consistency. So pure eventual consistency is asynchronous replication, write to a single replica and replicate that across the other replicas asynchronously, and read any replica, right? So we can read any replica, and that means we may potentially get inconsistent values. And what are we doing when we're tuning consistency, right? So we're tuning things like performance, we're tuning things like latency, right? Because if we have to go and write to a quorum of replicas, we're going to have a much longer time to perform our call than if we just have to go and write to one replica. Similarly, if we have to go and read from multiple replicas, we're going to have the same thing, a greater level of latency. We can trade that off, but we're trading it off by paying for it with some measure of accepting inconsistent data. So to summarise, DocumentDB is a preview service. You need to expect and enjoy change over time. So it is improving over time. You'll see new features come out. You'll probably pick up some bugs. I know I certainly have. Reach out to the team. They love to hear about your bugs. It's a really exciting service, and it's a really exciting service when you think about how can I really take advantage of that very flexible data model that is still fully indexed, right? How can I take advantage of a completely arbitrary but strongly typed and fully indexed data model? Right? I've shown you some examples with sort of the canonical e-commerce store. I've shown you some examples using material safety data sheets and other sort of materials information. Think about how you might be able to take advantage of that flexible data model inside your organisation or your applications. Thanks so much for coming along to Azure Conf and calling into the session. Hope to see you at an event somewhere in real life sometime in the future. Do reach out to me at CAULD on Twitter. Would love to hear from you, gather any feedback and so forth. Make sure you sign up and grab the free trial or use your existing MSDN benefits on Microsoft Azure. And thanks for coming along.